Huge pleasure to introduce Herman. I guess we haven't seen each other in a while. I'm not sure how much of each other we saw throughout the whole PhD. There was that pandemic in the way. I think Herman, more than any student I've advised, has marched by the beat of his own drum, to use a musical analogy. Taylor and I would give him lots of great ideas for papers to work on. He'd say, "No, I got this." We did this instead, which was fine. We didn't pay him very much, and it really seems to have paid off. I think he's just really knocked it out of the park on the job market. He's done amazing work. Can't wait to hear about it. So how do you think, Taylor?
I would just second all that. I mean, I think have been a very independent student. You've kind of already been running your own lab before even, getting a faculty position. So it's very, very exciting.
Cool. Yeah, let me switch the video to cool. Cool. So yeah, let's get started. Should I stand? Talk to you. Okay. Cool. So thank you so much for being here. So today I will be defending my dissertation on generative AI for music and audio. Oh wait. I should also change the microphone. Oh, cool. So yeah, before I start, I just want to talk a bit about myself. Do you know how to remove this? There's an option, right?
It's not at the remote.
This one, hide from. Okay, cool, nice. So yeah, I started as an undergrad in electrical engineering, and then I spent like 2 years at Academia Sinica as a research assistant. There's where I started to work on music generation, and then here I am at UCSD. And during my PhD, I've done a bunch, quite a few internships. So part of the dissertation was done during my internships at various companies. And also outside of research, I'm also I still not working somehow. So I think I play drums, and I also recently start to picking up playing the piano, which I'm not good at all. So yeah, that's how I ended up here doing my work on music generation research. So before I start, I'd like to talk a bit about the history, how I see how music and technology interact with one another. So, looking into the past, how music and technology is always interacts is always a two-way process. So for example, the classical music together grows with the violin and piano making industry. And also recently we have the introduction of synthesizers and also drum machines, which popularize the electronic music. And today we still have both acoustic and electronic music, which is part of a big part of the music that we listen to today. So and today, in the era of AI, there's a bunch of different applications, and we also see a lot of successful integration of how AI can be integrated into music performance on stage. But it's also beyond that, because music and audio exist in everywhere. So we have films, we have theater, we have gaming, dance, podcasts, and short videos. And also it extends to music education and music therapy. So, now in the next decade, with the rapid progress of AI, we are excited about how AI or the generative AI can be impactful on music and the audio industry, and also the various industries I'm showing you. And so this is how I view how AI and music and audio. In one way, new technology creates new art form. I'm excited about how AI and generative AI can bring to new experience, new interfaces, new instruments, or new experience that's powered by AI and bring to the music and audio industry. And on the other hand, new art form inspires new technology. So, there's with the growing momentum in the music industry about how AI is going to impact the industry, a lot of musicians are also looking into how how AI can bring to music and how, this need of new technology, new capability can enable new technology. So that's where my research stands. My goal is to empower music and audio creation with machine learning. And so an overview of my research is on how AI and music and audio works. So my research aims to answer two core problems, two core research questions. So first, how can AI help professionals and amateurs create music and audio content? So for this, I build infrastructures for music generation research, and I also develop, AI-powered assistive music creation tools that aim to help musicians to create music. And on the other hand, I'm also interested in knowing how can AI learn to create music and audio like humans do. So this is more from an AI perspective. So I study, I develop deep learning models for multi-track music generation. And I also study self-supervised learning, self-supervised multimodal machine learning for audio and music that mimic how humans learn to create music and audio. And today, I will be focusing on these three directions, namely multi-track music generation, assistive music creation tools, and finally, multimodal learning for audio and music. So let's get started. So the first direction of my research is on multi-track music generation. So here, our goal is to see how can we build better machine learning models for music generation. So this is part of the work that that was done before my PhD. So just to give you the context of why I'm interested in this direction. So here we are trying to tackle the problem of like pop music generation, but it's for shorter music excerpts. And so this is the first neural net that can generate multi-instrument music from scratch. So before this work, people are focusing a lot on generating, 4-part baccalaureates or simpler form of melody generation or lishi, which is just melodies plus the chords. But now this is the first time that we are trying to use deep learning model to see whether we can actually generate a full composition of multiple instruments. And so this is how it done. So this was back in 2018. So, there's a lot of progress in the last few years. And this was also featured at AWS Deep Composer. So this is one of the work that was done before my PhD. And so during my PhD, I also do an extension on that to kind of modernize the demo architecture that we are building. And we are also aiming for a much more challenging task, which is orchestral music generation. So for orchestral music generation, we are aiming for, a much larger set or much larger ensemble compared to pop music. And so this is still the state-of-the-art machine learning model for orchestral music generation, which was published at ICAS 2022. So, and this was done at UCSD. Cool. So an overview of this project is that we want to generate orchestral music of diverse instruments and we propose a new compact representation with multidimensional transformer. And this is what it sounds like. So as a preview of what we've achieved, we can generate much longer samples, which is important in orchestra music, because orchestra music tends to be, a lot more instruments, but also a lot longer than like typical pieces. And we also achieve much faster generation speed and achieve competitive quality of generated music. And this is important for orchestra music. And so how do we do that? So this is achieved by, something similar to ChatGPT. Basically, we are generating music using language models. So just a bit of background of how language models work so that you can kind of get a sense if you are not familiar with more than, NLP models. So this is actually how ChatGPT do, or maybe ChatGPT do a lot more, but I mean, this is the fundamental of how ChatGPT works. So the idea is that we collect a bunch of articles. So for example, here we have a bunch of Wikipedia articles, and our goal is to predict the next word given the past sequence of words. So here, for example, we have like a transformer is and then we want to try to, predict the next following word. So there could be several different options. It could be an electrical device, it could be fiction character, in the movie. It could also be a deep learning model, if you're familiar, and also it could be a family of genes, which I don't know before I Google that. And so, our goal or the goal of this machine learning model is to increase the probability that we can get these outputs. But on the other hand, we don't want it to output something like a type of food or a musical instrument, which it's not true based on the distribution that we observe in the articles. And so this is how language models work for text generation. And so once we have such a model that do this, probability modeling, how can we generate a new sentence? So it's very straightforward. We can basically do something like this. So we have a transformer insert, and then we let the model to guess the next word. And then we keep on doing this. So this is the simplest form of how we can generate text using these language models, but there are a lot more complicated sampling methods to be used. But this is the simplest form. But this is for text. How can we do that for music? So to enable that, we have to design a machine readable music language. So here in this work, we proposed a new music representation that can, allow me to model music, multi-track music using machine learning. So basically what we did is that we represent a music piece as a sequence of superwords. And so these superwords are, it's actually a tuple of 6 values. And there are several different fields that we have to insert the data. So the first the first field is a type where we, which actually like suggest what the word is. So it could be, a structural event like start of song, start of notes, or end of songs. It could also indicate that these superwords denotes an instrument or a note. And so the other fields actually basically just specify the note and instrument information. So here's an example so that you can understand it. So basically what we did here, we have a bunch of, say we have this music, even though it's presented in piano roll, but you can see it as like 3 different instruments played at the same time. And so we have like structural events, just as we in language modeling, we have like start of sentence and end of sentence. We have start of song, start of notes, and end of songs. And now we have a bunch of instrument events that show us what we are going to generate in this music piece. And also we have a bunch of note events that actually encode the data or the music that we are going to represent. So once we've done this, we can do something similar to what we have done in language modeling, basically just generating it's like a bunch of words following the others. And so it's like doing the next word prediction, but now we are doing it on this musical representation. And so this actually leads to the multi-track music transformer that we propose. So it's a decoder-only transformer, predicts 6 fields at the same time, which is different from typical transformer. And also it's trained out regressively, which basically means word by word or doing the next word prediction. And so I won't go into the details, but we are training this model on the symbolic orchestral database, which is a large orchestral music data set, and it contains various ensembles from choir, string quartet to symphony. And this is the result. Cool. So that's basically we are treating this machine learning model to generate music unconditionally without any intention from the user. Like maybe we want to specify the instruments, maybe we want to specify something to control the music. And so that's also one of the benefit of the proposed method, that what we just saw is basically unconditional generation, which we just put like a star of song and then the model just improvise and get a bunch of outputs. But at the same time, with the proposed representation, we can also do instrument-informed generation or generation condition on the instruments that we have. So the idea is that we just provide some prefix to specify the instruments that we want, and the model follows to continue this representation. And also we can also do continuation, like we can basically provide the first several bars to the model and let the model to continue it. And the benefit is that we only need to train one model to achieve all these different sampling modes. And so here are some examples. Say we can do instrument-informed generation. And we can also do 4B continuation. Yeah, so I guess you're laughing because you recognize what it is. So yeah, it's pretty cool to see how it, turn this like very Western style of like composition into a more Oriental flavor if you listen to the scale for the notes. Let me play it. So that's part of the result, but also there's another big part of this work is that we are looking into the magic of transformers, which is the self-attention mechanism. So as I said, like what we are doing in language model is basically doing this like probability modeling game where we want to, increase the probability of more probable words. And so like, you may assume that, the model now is doing something like this, like, looking into the past, like they are equal. But that's not exactly how we do it in, for humans. Like to predict this word, basically, it's much more important to know that this is a transformer because that's exactly the word it's describing. And the other words are basically just like telling you that it's a singular form or, more grammar-ish things. So, what we want here is that we have this like variable attention so that the model can learn to attend to different words prior to the current words. And we want to learn this from big data. And so here is an example of how music self-attention work. So this is in one of the prior work in a music transformer. And so here you will see a visualization of how musical self-attention work, and you see the colors and the links on how the model is doing when generating the music. So here you can see that when generating these nodes, it's actually attend to the first chord, but also attend to the current chord. And so, but this still, can we go beyond case studies? Because lots of prior work are actually looking into musical self-attention, but it still remains on the level of like case by case study of like whether the model is doing the right thing in this particular piece. And so we are interested in knowing whether we can actually achieve statistical analyses on musical self-attention. So here, we also propose a new quantity that can quantify statistically how music self-attention work. And so I won't go into details, but basically we show that the music multi-track music transformer model attends more to notes that are 4 beats away in the past, and also that has a pitch and an octave above, which forms a consonant interval. So, these are very basic as a musician, but it's interesting to see that from like learning from a large data set that the model can actually learn such a relative self-attention for beat and pitch from purely observing a bunch of data. So in sum, we proposed a state-of-the-art machine learning model for orchestral music generation, and also we presented the first systematic analysis of musical self-attention. So, any questions so far?
Yeah, hello, can you hear me?
Oh, yeah.
Okay, yeah, I had a question about the music representation. So, how do you decide like whether you should represent the music as audio, like in speech recognition, we simply just take the raw audio and do that, do any task, or do you represent the music as notes, instrument, duration, those kind of fields? Like, how do you decide between the representations?
Yeah, I think like both directions are super popular nowadays. So a lot of people also do it on raw audio, modeling. And I guess, sometimes it's not it's part of the decision making. So I guess one of the benefits for symbolic music generation is that it allows once you generate the songs that it can actually be editable, or like you can like musicians or the users can actually change the notes that are generated from the models. But I mean, the downside here is that we don't have the ability to get the actual sound that's at the end of the result. We still need to plug in some synthesizers or drum machines to get the sounds out. So I guess there's a trade-off, but I think the ultimate way is that we should do both at the same time. Ideally humans learn to do this. We listen to music as raw waveforms, but we somehow understand it as symbolic music, like a sheet music, and we understand it, but it's like a combined process of modeling acoustic information and the symbolic side of music at the same time. But currently, I think there's a mismatch, and people are doing it parallelly. And I think the next frontier would be, how to combine those. But they both have their advantage and disadvantage at the same time.
Sure,
Cool.
yeah, that
Yeah.
answers my question. Thank you so much.
Sure. So let's move on. So that summarized the first part of my research, multi-track music generation. And next I will move on to assistive music creation tools. So here we want to develop assistive music creation tools that's powered by AI. And so here we want to answer the question of how can AI help with professionals and amateurs create music? And so I will first talk about this project on automatic instrumentation, which was presented at ISMIR 2021. And so this is the first ever machine learning model for automatic instrumentation, which is funny because we are the first to work on automatic instrumentation because this is a newly proposed task. So this is a joint work with Chris Donahue and my advisors at UCSD. So what is automatic instrumentation? So the goal here is basically to define it technically is dynamically assigning instruments to notes in solo music. And so why do we want to do this? So think about in keyboard playing, we have this zoning ability that we can assign different zones on the keyboard to different instruments. But this is not ideal for performative performative use case where, musicians have to rearrange their compositions so that you can fit into this zoning capability of the keyboards. So if we can do this, use a machine learning model to dynamically assign instruments to all the notes that are being played on the keyboard, it will allow the musicians to play naturally, but still have the ability to play multiple instruments at the same time. And on the other hand, it could be used in the offline setting where we have assistive composing tools that, some composers that might be unfamiliar with a new ensemble that they have never composed for. And so this could be helpful as like an initial step to, kind of assign the instruments or give some suggestions to the composer so that he can arrange for a different ensemble. So, but the question is that how can we acquire pair data? Because, there are not many, paired like Sony music with the actual instrumentation, the actual full piece with instrumentation. So in this work, we turn to another approach that we try to do this without pair data. But still, we want to synthesize some kind of pair data so that we can train the model. So the idea is quite simple. We have many, multi-track music data sets that we have a lot of different instruments. So here, we basically just blend them into turn it into black and white, like as if it's like played by one single piano. And so now we are doing this sort of like colorization task where we want to train a model to predict the instrument for each single note in this piece. And so, from a machine learning perspective, this seems like a very naive way to do this. It's basically just like taking all the notes as a sequence and then try to predict the colors or the instruments here. But this is interesting because once we train this model, during the inference time, we can do something like this. Say we have this mixture played by only guitar or piano. And then we can just use this part separation model, which is not trained for automatic instrumentation, but we can achieve something like this. Which is pretty cool because it's basically just a sequential classification in the terminology of machine learning. And so there are two types of models that we use in this machine learning setup. So we have the online models, which basically can only look into the past, that we have no access in the future information, which is useful in the intelligent keyboard or real-time performative use case. But at the same time, we also have offline models, which use BioSDMs that you can look into the future and also the past, which allow you, provide more context to the model, and the model usually perform better in this offline setting. And that could be used for composing tools, but it could not be used in performative, use case, because you never know what the musician is going to play next. And so here we have a similar representation that similar to what we just saw, representing notes as time, pitch, duration, and also we have frequency, beat, and position. And the goal is to make it into machine readable format. And we tested on 4 different, various genre of data sets. And so here's one example result. So here's the original composition of our original instrumentation of this song. So what we can do is basically remove all the colors and let the model to recolor again, and let's see what the model do. So here we have. So as you probably noticed, the model do a great job on, assigning all the low pitch to the bass, and also, the higher pitch to, the clustering of the notes are basically correspond to how we cluster these notes. And also we have the BIOS here. So it's interesting to see, these longer notes are assigned to piano, which doesn't make much sense, but also, you have like orange notes that's clustered. So basically in the model notes, like these longer notes to be assigned to the same instruments, but these shorter notes played in the chords should also be assigned to another instruments. Cool. And so we have a lot more results on like also barcarolle, string quartets, and also GAN music. And so in summary, we proposed the first ever machine learning model for automatic instrumentation, which is also a new task. And this has like potential applications in assistive recreation tools and also intelligent keyboards. Any questions so far?
Yeah, I have a question.
Mhm.
Since you brought up the analogy like GPT and language modelings,
Mhm.
one of the impressive things it can do is write me a poem about peanut butter and jelly in the style of Shakespeare. I'm wondering how much what you're doing here with different instrumentations could be changed to something like you have the score for a piece, but you really want to render it differently, not just the choice of instruments, but play me Beethoven's symphony in the style of stride ragtime piano. You sort of
Yeah. So I
take me
guess
on
that's,
the floor.
yeah. I will talk a bit about it later in the next work. But also there's this one of the limitation here that we are only looking into, symbolic music and the instrumentation only. So, so synthesizer or, how we actually turn these sheet music into audio is not part of this work. So I guess there are like two questions. It's one, like, can we do, this kind of like style transfer in terms of the timbre or how we play it. I think people have been working on that, and I will talk about it later. And also the other one is, what's the other one? Okay, I've got the other one.
No, that's great. That's great.
Okay, cool.
I understood the questions differently, so I'm not sure. I thought the question was, let's say you have something instrumented in one way and you want to instrument it in another way, change the instrumentation. So with the hint, you can do this with the hints. I mean, you can take a score, reduce it to piano, and then say
Recreated using
other hints.
I see. Yeah, so
if that was the question, I'm not sure.
Yeah, so in this work, we basically have a fixed, target instrumentation, but the model at the same time has the ability to choose whether they want to use that particular instrumentation. And so, I guess to achieve what you're proposing, I guess like the ultimate way is that we have to train everything at the same time, have a bunch of different genres, and the model has to understand how, orchestral work and also how pop music work at the same time. But currently, we are basically, training the target as one single genre, and the instrumentation is somehow fixed, even though, in orchestral music, there could be different ensembles, but still it's mostly classical.
So your entity recognition of one set.
Yeah, it's like a specific genres, basically. Yeah. But still, I guess it's possible if you can train everything at the same time, even though I guess there will be a lot of hints from the input that kind of suggest that this is a, pop music. So to achieve that kind of like zero shot musical, style transfer, we probably need to do something more than, simple, just train everything without any modification. Because the model, look at this mixture, it's kind of obvious that this most likely is like a pop music rather than a classical music.
Well, this doesn't generate new notes either. I mean,
Yeah.
pretty
And
basic
yeah,
piece.
Yeah, that's another point that I want to add. So, one of the biggest limitation here is that we don't actually add new nodes. We don't remove nodes. We are basically using the same node set. And then we just, give colors or give labels, give the instrument labels to that. And so it's still far from actual rearrangement or, orchestration or even like piano summarization. It's just focusing on the instrumentation part.
But that's like partly because in this kind of data set, you can build as big of a data set like this as you want.
Yeah.
Whereas like creative arrangement data sets are like
Yeah, exactly.
so impossible to construct.
Yeah. So yeah, I guess the biggest problem here is that how we can get like pair data. And yeah, I believe like Zach also work a lot on like piano reduction and also, orchestration. So it's just super hard to get these data. And this is one of the way that we use, without pair data, but we somehow create this synthetic data set that allow us to do this like first task of instrumentation, and we can see whether we can extend it to rearrangement, adding nodes or removing nodes, which will be much more challenging, I believe.
Well, if you can get us that Beethoven to ragtime data set,
Yeah,
I think
Yeah.
we can do it.
maybe that,
Yeah.
that's how I interpreted the question too. It was actually
Yeah,
about,
yeah.
like, recomposition to some extent.
Yeah. But again, I think it's still far from that, but I think it's definitely possible that we can like move a bit forward. So,
But I think the closer thing to that would be the multi-track music transformer paper.
Yeah, because like in that case, we are, have a much more diverse ensembles in the space that we are modeling.
And you're generating notes rather than just.
Yeah, exactly. Yeah. And yeah, recently we are also looking into like training a GPT-like model on a much more complex genre set. So basically MuseScore forum. So we are training music like language models on MuseScore. And so MuseScore is like a huge data set that has like so many different genres. And so in that sense, we could potentially do zero shot style transfer in that sense. Cool. Wait, why do I have this? So yeah. So yeah, I also in this direction of assistive music creation tools, I also work on score to audio synthesis, where it's also answer part of the reason, answer the question that we are modeling how different performer perform differently given the same sheet music. So we focus on violin synthesis, and we adapted from fast speech, a text-to-speech model. So this is different because. So this is how it sounds like. So you can definitely hear that there's a slight pulse or like slower BPM when you reach the highest note. And so, this is different from text to speech where we have potentially, actually we have a bunch of concurrent notes or polyphony in music that we have to handle. So we have to propose new techniques so that we can handle polyphony in the text-to-speech model. So you can definitely hear the polyphony that the model is actually generating multiple pitch at the same time. And also we are learning how different performers do perform these the same sheet music differently. So I won't go into details, but this is also one of the work that I've done, which is published in, I guess, 2020. Sure.
Yeah. I guess I just remember about it, but like how accurately is it actually rendering the notes? Like, is it hallucinating notes that shouldn't be there or dropping them, or is it actually pretty accurate?
It's pretty accurate. It's
That's
like,
awesome.
yeah.
Really cool.
Yeah, so it's like PDS, like you won't understand like new words that's not part of the input. So the input is the sheet music and the output is basically waveform. Or here we are generating the mail spectrum. So yeah, I guess one of the key contribution here is that we are doing this end to end. It's not end to end, but I mean it's like we train 3 models basically, but it's the first time that we can do from the actual raw score to the waveform using like a series of models. So people have been doing like piano like performance rendering, basically getting the expressive timing of the notes, and also people have like, you know, synthesizer, vocoder, but this is the first time that we can actually do it in one single series of models. Cool. Yeah, so that's the second part of my research. And now we go into the last part of my research, which is on multimodal learning for audio and music. So here we are interested, I'm interested in, you know, how we can build AI systems that learn audio concepts like how humans do. So this is a lot about self-supervised learning, where we are trying to learn sound separation and synthesize from videos. So I will first talk about the later work that I work on text to audio synthesis, because it's on generative models. And so this is the first text to sound synthesis model that can be trained using only unlabeled videos. So this is a work that I did during an internship at Adobe. So what is text to audio synthesis? So the goal here is that given the text query, we want to generate the corresponding sounds, or you can think about it like Foley sound synthesis, basically. Cool. So what we want to achieve is, you know, given the short text query, and we want to get the sounds like automatically. And so this could have a lot of like potential application, you know, in filming, even on YouTube, when you are posting something that you record some audio, but you kind of miss one of the audio, or the audio is corrupted, then you can actually add like Foley sounds to the videos, or, you know, different type of music and audio content that you want to create. So why do we want to do this using like videos? Because like text to sound generation, like the more obvious way is that we can simply grab a bunch of like text annotation with sounds. So I'm interested in this because for me, I think it's not supernatural for humans to do that. You know, there's no like dictionary telling you like what does the fox say. Like at least for me, the more natural way for me to know what's the sounds of fox is that we go to YouTube and then we just Google, you know, fox sounds, and then what you get.
Подожди, я тебе воды принесла.
So, you know, you see how humans are so capable of like isolating all the noises, and also, you know, look into the object and identify the main subject of the thing, and then associate the sounds that you hear, and also the object or the animals that you see in the videos. And so here we are interested in this idea, like, can machines learn to synthesize sounds from just watching a bunch of noisy YouTube videos? And so here, since we are using YouTube videos, what we did is basically we first trained an image to audio synthesis model. So, you know, remember that we are actually doing text to audio synthesis, but we have to train an image to audio synthesis model first. So we start by training an image to audio synthesis model. We take a video from YouTube, and we have the, you know, video, like a bunch of image frames, and also the corresponding audio. And so what we did is that we trained a conditional diffusion model that take the input, one of the frame from the video, and we, you know, encode it with clip image encoder and use it as the condition to condition this diffusion model. And so this diffusion model is trying to generate the spectrogram given a like condition, or, you know, given the image frame. Oops. And so here we are using clip image encoder because we want to actually use the text encoder later. So just a bit of context of what clip is. So clip is contrastive language image pre-training. And so the goal of clip is that it's basically a pair of image encoder and text encoder. So clip is actually two models. And so the goal here is to learn the shared embedding space for image and text. So for example, we have cat, the image, and also the text cat. And we also have dog image and dog, the text for dog. And so we have a bunch of different representation. And our goal is to make closer the image and text representation for the embedding for cat, and also the image and text embedding for dog. And we want to make everything farther away. So once we train this such a clip model, that what we get is basically a shared embedding space for image and text that has the same semantic meaning in image, in what we see and what the text describes. And so that's the interesting thing here, that because we are using clip image model here, we can actually do something, we can do this zero-shot transfer modality transfer, where we basically, during the training, we have image as input, and at the inference time, we just switch to text input. And so since we're using this clip model, ideally, the image and text embedding should be close enough. But unfortunately, when we look into the actual, computer cosine similarity of whether they are close enough, it's actually only giving you like 0.2, which is fairly low, in terms of like cosine similarity. So basically that means that there's a huge modality gap in clip. And so what we propose here is that we can basically introduce an additional diffusion prior, which is used in the DALI 2 paper in this paper. So basically the diffusion prior model, it's also pre-trained on the large text image data set. So the idea of this diffusion prior model is basically generating a fake image embedding based on the text embedding that we have. So that's the goal of diffusion prior. So you can think of it like an imagination task. So given this text input, like a photo of a train whistling, and the model, the diffusion prior model is trying to imagine adding more context, tiny nuance in the image that could be in the embedding. So, text is a much higher level semantic representation, but image has a lot of details. And so diffusion prior model is trying to fill in the gaps or fill in all the nuance in the embedding. And so basically what we've done is that what we are interested in is the audio and text correspondence, where we leverage the visual domain as a bridge. So we want to learn the audio text correspondence, but we have videos that provide free audio visual correspondence. And at the same time, we have this clip model that give us, pre-trained vision language shared embedding capability. And so this way, this is how we build the bridge to get the desired audio text correspondence. And so the benefit is that we don't need any text audio pairs, and also it can be scalable to large video data sets. And so that's what we did. So we have two YouTube data sets. So one is the music data set, which contains a bunch of music instrument play videos. And we also have this much noisier video data set with diverse sounds on YouTube, which is called VGG sound. So, these are much more high quality because those are people recording themselves playing music. And these are, more daily life videos that you see on YouTube. So here are some of the results. So what we can do. Cool. And also because one of the first thing that we did is actually training this image to audio synthesis model, and then later we use the diffusion prior model or do the modality transfer to achieve text to audio. And so we can actually also do image to audio synthesis with so you can imagine both the text to audio synthesis and also the image to audio synthesis models could be potentially applied to fully sound generation or filmmaking process. And interestingly, even though we are not focusing on image to audio synthesis, it actually achieves state-of-the-art, then state-of-the-art image to audio synthesis performance. So in sum, we proposed the first text to audio synthesis model that requires no text audio pairs because we are training on, self-supervisedly on large video data sets. And we achieve strong text to audio synthesis performance. And we achieve state-of-the-art image to audio synthesis performance back then. Any questions so far? Cool. So this is on the text to audio synthesis. And we actually first explored this idea of, self-supervised learning from videos on another task, which is sound separation, which is not generative AI. But that's one of the first work that I did to kind of like examine whether this idea works. So in that work, what we want to do is basically text query sound separation. So something like this. So we have this like mixture, noisy mixture. So it's quite obvious what we want to do. So maybe we have a query like we just want a harpsichord sound and that the model can do. So there's still a bit of noise. Yeah, but basically the model did a really great job on like separating these sounds, and these again is only achieved by like watching a bunch of videos only, and that was published at iClear 2023. Cool. I won't go into detail, but still, like first text query sound separation model that can be trained using only unlabeled videos. Cool. Any question on this? It's very brief introduction, and it's not generative AI, but still very cool. And I think it still can be applied in a lot of like, filmmaking process. So still part of the audio creation workflow, but it's not generating models. So to conclude, I have introduced several examples of my work on the 3 direction: multi-track music generation, assistive music creation tools, and multimodal learning for audio and music. And there's a lot more. These are various publications behind these blocks. And also I have done some work on infrastructure building for music generation research that I couldn't, I don't have time to cover today. So, if you're interested, check out the papers, then you will see all the details. And, also like open science, open source. So all source code was made open source with MIT license whenever possible. Some of the works are in industry internships, so I couldn't release it, but I will release all the model if it's possible. Cool. So finally, I would like to talk a bit about some future direction that I'm excited about. So, again, how AI and music and audio interacts, I think it will be a two-way process, as I talk about in the introduction. So on one way, I'm interested in, how can AI help professionals and amateurs create music and audio content. And so, as the AI progress, now it's super exciting to see a lot of work on multimodal generative AI with music and audio. So imagine we can have not just text, image, we could also have video input, we could also have like, EEG signals or like a lot of different possibility with the multimodal capability, and also, interactive AI tools for music and audio production. And on the other hand, like how can AI learn to create music and audio like how humans do, more from the AI perspective? So I'm interested in looking into human-like machine learning algorithms for music. So I just talk a bit about it, like, symbolic modeling of music and raw audio modeling of music. I think there must be a way that, how humans learn this is basically through both direction, like we receive like audio inputs, but we also have the understanding of sheet music. So in that way, if only if we can model like machine learning for music in this way that we can actually achieve more human-like machine learning algorithm for music. And also I'm interested in seeing how interactive human AI musical creation can work. There's a lot more recent music generative model that being proposed. And so, it will be impactful, and I want to see how like human and AI can co-create music. So yeah, some details, we have Sora nowadays, like in February, but these are videos without sounds, which is pretty awkward. So, one of the things that we've been working on recently is to build a data set to achieve, trying to add music to these video generation models. So it could be like just from video to music and sound effects, but it could also be, text to video generation with music and sound effects at the same time. And yeah, and also like here's one example of like multimodal generative AI for news. It's very interesting because it's related to the point that I want to make later. So this is one of the model that's proposed by at Primary, in Surrey. And so the idea here is that they use ChatGPT, GPT-4 to give it the prompt of this and try to generate a script that can execute these like pre-trained large audio models to generate the sounds. Let's listen to the example first.
Welcome to Mars News, your source for interstellar news and updates. We have a significant development to report today. Humans have sent a Lightspeed probe to Alpha Centauri. Now let's connect with our on-site reporter to give us a brief overview.
We're here at the headquarters of the United Earth and Mars Government Space Exploration Division, where the probe was developed.
Cool. So this is interesting because the model is actually doing this like instruction and then use ChatGPT to get this audio script. It's encrypted as like JSON file in ChatGPT. But basically what we want to get is such a table that we can later use these pre-trained generative audio models to, synthesize the sounds for, like TDS for the reporter, or, some sound effects, some music that specify the, duration and the starting points. And so this would be important to get interactable intermediate results that you can actually interact with. And so this actually corresponds to controllable generative AI. So you can see how it can be integrated into professional creative workflow. And so this work is like one of the preliminary study where there's no actual data training. There's not actual machine learning, like they didn't collect a data set to achieve this. Basically, what they did is like coding ChatGPT doing that zero shot. But I believe there could be a lot more to be done here in both like film, music, film audio making, and also music creation at the same time. And also, there's a lot of discussion going on licensing training data for generative AI. So here are some of the examples that what people have been doing in the visual domain. So, all the companies are partnering with stock image providers to train their own models so that they can progress with more cares rather than, just grabbing a bunch of illegal images to like infringe the copyright of the copyright holders. And, so I believe in music industry, we also have to do something similar to this approach, that we have to progress with cautions. And also one thing interesting is like attributed AI generated content. So this is one of the work that's been done in image generation. So, we have a bunch of like generated samples, and what people have proposed is that we can actually train a model to undo this like generation process to look into what are the reference in the training data that contribute to how you generate this sample. So this is interesting because like you can imagine like in the future, maybe there could be a potential business model that you can, basically pay the copyright holders when you actually reference their work in creating your own work. So, I think it's an ongoing debate or discussion, but still there are some ways that we can potentially create a new business model or how it could like benefit both sides of the situations. And so, people have been looking into how it can apply to music also. So again, these are my future direction that I'm interested in. Cool. And with that, finally, I would like to thank many people in my PhD study. So first, big thank you to my advisors, Julian and Taylor. Yeah, I do remember the first meeting that I had with you. So like first year is like in the EE and I transferred to CSE. And so yeah, it was really nice that like you have me as your students, and I learned a lot from the process. And even though I did a lot of internships, but still, I think the flexibility that you give me that actually allowed me to grow, into an independent researcher. And also thank you to all my collaborators. A lot of them are from industry, and also, a lot of them are from academia. What else do you have? And a special thanks to Shlomo, who helped me a lot in the job search process, and also Eric at NTU, who actually helped me a lot during the job search process. And also thank you to my internship mentors. A lot of work that I presented today are the results that I did during my internships at different companies. And also thank you to my lab mate. It was very fun. It has been really fun in the last few years in the Berg lab and also Macaulay lab. And thank you to my family, especially my wife, who is also defending soon, the week after next. And it was really nice to do PhD here at UCSD together for the past 5 years. And yeah, financially, thank you for supporting my PhD study, and also various internships and also fellowships. And thank you, UCSD. And so next chapter, I will become an assistant professor at University of Michigan in the Department of Performing Arts Technology under the School of Music, Theater, and Dance, which will be super cold in winter, but yeah, I might miss the sunshine here. So with that, thank you so much for coming today. I hope you actually see something interesting from my talk.
Cool. Great talk.
Questions?
Audience questions first, I guess. Oh yeah, we're supposed to moderate, right? Yeah, what would we could do in-person audience questions, then Zoom audience questions? You see what's on your microphone, like that is everybody in chat.
Yeah. How do I?
Or just stop screen share.
How do I get back in control? I don't even know how I can stop sharing. Anyone knows? Oh,
Who's there for a second? Gone.
no, I think it's this.
They're down the bottom.
Chat.
Herman, I have a question.
Mhm.
Just want to poke your brain a bit. So like on like the clip step stuff and the clip sonic, like I know it's kind of similar to some of like kind of like using like text as kind of like the intermediary. And I know that there's also like some other work too, like Facebook is it with like the image bind where it's using like images as the intermediary. And do you feel like considering like for like audio visual representation learning, do you feel like text do you think is like kind of like the best bridge, or do you feel like working in something that's like also a perceptual signal like might make a bit difference, whereas like videos and audio are a bit more similar maybe than like raw audio and text?
Yeah, I think definitely text is not enough in terms of, describing the scene, and, especially in film making, it's like there's a lot of nuance going on in the scene. And also think about like sound effect generation, like if you want to do footstep generation, like without looking into the scene, how you can actually produce those like actual timing of those footsteps. And also the same as like dance, like if like people are dancing to the music, then you have to predict, the BPM and also like how their movements correspond to the music. So I guess there's a lot of different things that's not possible to be described it in the text. But people are doing this because now we have like text music model. We also have video text model. Again, like what we want, I guess it's more like a combined way to do that. We have video to music generation system, but we also want to use the text to guide what's the style, what's the ultimate, like, I don't know, vibe of the music or the audio that you want to create. So I guess it's a mixture, but I believe it will be super challenging to actually achieve that. And in terms of data set creation, but also like modeling, how we can have like parallel information that potentially could lead to some conflicts. But I guess that's the same for all the multimodal learning. People are facing this challenge nowadays. Like if you want to have like multiple different inputs from different modality, then it will definitely become an issue when you want to do that. But it's a must in a lot of applications.
No, yeah, totally. Thank you.
Cool.
Any questions from audience in the room?
I have a question.
Mhm.
So how did you evaluate the quality of generative music?
Yeah, so lots of the work that I done is like, I think subjective evaluation is still the key. And so most of the work that I will definitely do subjective listening tests. And there are some like automatic, evaluation metrics, but I think it's still huge mismatch from those metrics to the actual ratings or human perceptions. And yeah, so I guess that's the situation currently. And also like in terms of like subject listening tests, I kind of I think people have to specify what they want to evaluate during the music, the listening test, that whether you are rating the interface or rating how good the music is, or more importantly, I think it's interesting to see like nowadays we have a bunch of like different music and audio generation models, and they are performing really good. But I guess the next frontier of what we want to actually do is like how many steps that we need or how much effort we need to actually like fulfill our intention in creating the music or the audio that you want, rather than these models are very good at all the audio quality, but I guess the alignment of like human intention, user intention to the actual model output is the key to be solved. And I don't think current model do well on that, even though like if you remove the text prompt, it looked good. But once you have the text and like the intention of the user, I mean, text is kind of limiting the space that we can like provide to condition the model. So yeah, I guess that's some way, still not solved, but that's how we can potentially evaluate these systems.
So I have a question about like the earlier part in the talk. So when you show the orchestra generated music, so when I listen to the pieces you show, I have a strong feeling that the tempo are all very fixed.
Oh, yeah.
And also like there seems to be like clear pauses between each note, which sounds probably like just like when we are talking or we are reading. Is it something related to the text
the pauses? So first, we didn't do BPM, so it's like a fixed BPM. So it's like sheet music and render without any performative like attributes. So it's like sounds like MIDI basically. And
it's like temporally quantized, right?
Yeah. And also, but potentially, like the deeper performance thing that we can potentially use like synthesizer to model how it can be performed in a more natural way. And regarding the pulse, yeah. But regarding the poses, I'm not sure whether what you're talking about, like
Can Deep Performer do multi-instrument simultaneously?
not at all. I mean,
If it could though, you
Yeah.
could totally hook them up, that'd be
yeah,
cool.
but yeah, so you know, yeah, maybe the first question first. Like the pause. What do you mean by the pause?
Like if you go back and play the sample,
Okay.
so there are, maybe it's something related to, also because the tempo is very
I
fixed.
bet it's
Yeah.
because of that, yeah.
Yeah,
But I'm
Yeah,
really
yeah.
curious to listen
You
to.
mean it's just not like balance?
It just sounds a little too like
very
machine-like.
discreet.
Yeah,
Robot.
right. Yeah.
Very
That's
robot.
what it is.
You're playing a string instrument.
Any
the notes
meeting
would overlap a little
playback
bit.
sounds like.
Yeah.
this.
Yeah.
This.
Okay,
Just-
you're referring to the instrumentation
Yeah,
paper, not the not
This
the
this
transform.
example?
the
Other transform.
orchestra,
The orchestra.
yeah, the MMT, I think.
Yeah, that was in the.
Yeah,
this
this was
one.
in
Yeah,
yeah.
Uh,
I
Are you
guess
talking
it's
about,
just
like,
yeah.
The pauses between phrases. I think those are by design, but it's just that they sound kind of machine-like.
Yeah,
It's
yeah,
so
yeah.
regular.
It's like
Yeah.
super meaty. Like,
So what I had in mind for pauses was actually the last example,
oh,
but
this one?
yeah.
I mean, it's the music itself.
You kind of,
Yeah.
it's conditioning on the
Yeah.
first bar.
It's got
Yeah, so this
accent,
like, yeah.
No,
So yeah, I mean, it sounds like
But-
this. I mean, yeah.
which one is that?
That's Mozart.
That's
Yeah, it's
Mozart.
Mozart, yeah.
Okay,
Here,
cool, okay.
this is.
Yeah, I guess it's probably more about the
Wait.
fixed tempo.
Yeah,
That
yeah,
kind
yeah,
of
yeah.
Kind of knock music? No,
Yeah.
that's.
Yeah,
what
it's
that
not
is?
music.
That's what that is?
Yeah, exactly, yeah. I was surprised.
Has nothing to do with the text language model.
That's what
Yeah.
I think, so, yeah, that's what I mean.
Yeah, so I guess the model actually learned something about that particular example. So, you know, there's some pause there and it actually recreate that. So I guess it's actually nice to see the model actually having those pauses because that's actually part of the original music that it wants to continue.
Yeah,
And
Yeah.
how about the tempo, like the fixed?
Fixed tempo is basically a MIDI files. If you play MIDI files, it just sounds like
But
that.
in the example,
Yeah.
you're comparing generated output synthesized from.
Oh, yeah,
space
yeah,
and
yeah,
MIDI
yeah.
To a real
Yeah.
orchestra playing the ground truth.
Yeah. So the Mozart one is like, you know, it's,
So if
yeah.
you converted the real orchestra to MIDI and then synthesized it in the same way.
yeah,
The two
yeah.
pieces would sound more characteristically more similar.
Yeah.
It's like, I think text is the right analogy. It's like you can generate text, but that's not the same as speech. Right, and then you can render speech in a very flat way without like doing anything interesting with the prosody, or you can render it in a very dynamic and prosodic way. And like a MIDI, like a synthesizer in your DAW is like the very rigid way. It's just.
Yeah, we could have played an orchestra to play the generated music.
That would be.
Yeah,
cool.
that would be
That
cool.
would be great.
Yeah, and yeah, regarding the performer, the work, so the way that we actually can do this with the data is that we basically look into public, like public domain or like CC license work on Bach sonatas and partitas, because there's many work on Bach, like many recordings on that. But for other music, I mean, it's kind of like impossible to get any public domain data and also, you know, even CC license data. So that's why we focus on violin synthesis and also we do only on Bach. So potentially, if you have a bunch of data, then potentially we can also do data for different instruments. But I doubt, yeah, because you know, that's their copyright. I mean, you know, classical music, these music are, the music itself is in public domain, but the performance is the key to these recordings. Yeah.
But I think it alludes to a bigger problem that, you know, to make music really, you know, the way we feel is, you know, expressive.
Mm.
You actually have to render it.
Yeah,
you render
exactly.
it with humans that add this extra layer that actually makes it.
Yeah. And
so
yeah.
someone's score is still a sketch.
Right.
Yeah. I think also related to one of the interesting thing that could potentially be the future work is that like personalization. I think, whenever we talk about copyright, like we are like, we don't want to infringe the copyright holders' right on these data. But what if they want to use these models? Then it becomes interesting because like, say you have like ChatGPT or like large backbone models, like foundation models for music, but potentially if you are the copyright holders and you want to train the model or fine tune the model on your own, piece of work, then potentially these personalization will be a very interesting frontier for like these current models. These models are not, adapted to users' intention or their own styles. But, if we can have such like personalized music generation system, or, even everything could be personalized in some sense, and it could be interesting to actually add a more personal, touch on these models.
I think it's also interesting that, in speech, there's a lot of work on.
Yeah.
expressing
Only
speech,
speech.
And not so much in the music domain.
Right,
because-
like that, this is like the first like speech synthesis system. It's really cool.
In this work, actually, we have like different performer, and even though it's hard to, disentangle, like, because we have limited data, once you have a lot of data, you can actually like distinguish between, how to play this music or how to play this music in this particular style.
So I guess it would be performer specific.
Yeah, exactly. And
So it's like.
so we do have like, and also one of the performer, interestingly, they play in Baroque tuning system. So actually everything is like one pitch lower. So, when you put that, use the model. So basically we have an input as the performance ID. So it's similar to text to speech. You have the speaker ID. And whenever you put that performer, it will be one pitch lower.
They're like
which is
in the
interesting.
drop D or whatever.
Yeah.
Are we committee questions? Committee questions. Public committee. Public committee. Like kind of coming back to that though, like I agree, like this is really interesting that like learning kind of expressive performance. And I understand, that like data is a limitation. Do you think there's an opportunity to kind of combine the ideas from some of your multimodal work? Like, is there a way to kind of get away without parallel data to learn a better performer?
Yeah, I mean, definitely. But it's require a lot more, effort, so in this like Clip Sonic, we actually do like kind of like music synthesize. But it's like playing violin and without knowing anything about the sheet music, and like there's no input of the sheet music. And so potentially I think it's possible, and people have been doing sort of like motion to music generation-ish thing, but I guess it's still far from realizable currently.
I see what you're saying. Yeah,
There's a lot of challenges.
The analog would be like a video of somebody playing or something.
Yeah, I think the opposite way is
Yeah.
very challenging in some
Yeah.
sense, like even looking at the recording of the video and to see what the sheet music is actually playing.
Right.
But
and
I think there's a
you don't really have one side of the pivot, right? Because you don't have like sheet music to video or like I don't know what that
I
would
think it's
look
possible.
like.
I mean,
Okay, maybe.
if you get these fair data, you can actually do beat synchronization, and also you
But
can.
then you might as well just align the audio with the sheet music, right?
Yeah, but
Alright.
still you can learn that association. Yeah,
I see.
so I guess yes, but not trivial.
Yeah, that makes
Yeah.
sense. I have one more question. This is like not really a real question, but it's just
Mhm.
kind of like related to one of the things I think is most exciting about your work, and one of the things that I've always just been interested in about music technology. So like one of the things I really like about your work is how it's really tool driven. Like you're actually building new interfaces that musicians might want to use. Like these feel like, in a way, like new instruments, like new music technologies, rather than some kind of like black box, like big just generate music without thinking about like the tooling of it. And I'm not a musician really, I'm not really a musicologist, but one thing I feel like I've observed that may or may not be true about music is that like with each wave of music technology, very quickly the art form will kind of like gets interested in the cracks in the technology itself. Like you think about like the development of like amplifiers, like very quickly like tube distortion and then like solid state distortion become part of the vocabulary of music. You think about like early tape echoes, like the tape warble is now something that's sought after that people like use to create new effects. These are cracks in the technology. Like if you think of this, like neural deep learning is like the next wave of like music technology. What are the cracks going to be? Like, what have you seen? Like, are there creative potentials for the ways that these technologies distort and fail, or are they different somehow? From that
yeah, it's definitely. I mean, when I'm actually sad, like when the model become more and more, stock music like, it's like less fun, to be honest. And so I guess there are some interesting like characteristic of like early generative music in that like the timbre is not stable.
Okay.
It's very interesting. And I think DataBots has like a never ending YouTube channel on like metal music generation, which is really cool. And listen to those examples, it's not like perfect, but I think it has its own characteristic, and that's kind of marked the early AI music sounds. And also for now, I think there are still a lot of potential, say like personalization. One thing interesting is that overfitting is not a good thing, usually considered by machine learning, researchers. But what if you just want to explore the limits? Like you can train a model and then just overfit it completely on your own work. What is the extreme case about your work going toward the limit? It's like distortion. Like people are using distortion to create some vibe, but now people just like overdrive to max. And so it's something similar. Like these models have some parameters that could be potentially leading into some interesting.
Turn it up to 11.
Yeah. And also a lot of the current machine learning work is, interpolating between different genres, different things, but it's still mostly inside the distribution. And, there are some literature in the creative, computer creativity study that you are actually doing extrapolation. So basically doing it the opposite way. So think about like in classifier free guidance, if you do it in the other way, you can actually like do something other than the going toward the average mode, but the other way. So going outside of the distribution. So I think that kind of like,
what does that sound?
Yeah, it just sounds like something more more noises. I think once you train the big enough model, like whenever you go toward the boundary, it's become more interesting. Basically, so I guess there is some ways. So like we build tools and hoping people to break it and to see whether we can do something useful.
Thanks.
Yeah, I think that's how it is.
Great answer. Cool.
Any questions from the Zoom folks?
I'll ask one. Yeah, one of the reasons ChatGPT can write such great imitations of New York Times articles is because it was trained on, gazillions of New York Times articles. But of course, the New York Times and the writers who wrote those articles don't make any money off of ChatGPT. And I wonder if you worry about something like this for music, It sounds like you have something that eventually could, create a new album of Beatles songs or create music, and yet it's only because it's trained on the musicians, who did the original work, but they're not in really line to have rights or anything like that. I know that the goal is to help musicians, but the question would be like, do musicians are there two sides to this research that you have to sort of keep in mind?
So I think it's definitely two sides. I mean, some established musicians might be opposed of this idea of like training music models on their copyright material. So, I think it's definitely not a way that we can just simply train these model without the permissions. And one thing tricky here is that for the current copyright, we don't actually have this like, people are training image generation model on stock image data set. But I mean, in the stock image copyright or the license, it doesn't actually have the ability to grant you access, grant you permission to do the machine learning training, things. And so I guess on the, copyright side, we have to, get an updated version of how copyright works, and then we think about how we can get these like stock data sets for training these models. And on the other hand, I think personalization is the way to go when we want to do, that actually serve the both sides. Like we can potentially like train a large foundation model on stock music data set that we actually have the license or the copyright to train on their data set. And, in this process, there could also be some business model that I just talked about, like attribution, that potentially these could lead to profit, going back to the actual content provider that's inferencing the work that you are generating. And once we've done that, like we can ship the model to the user side, and potentially you can provide your own data, or in whichever forms, like what inspire you the most, and then you get the personalized version of your own system. So I don't know whether it will become that shape. I think that's one of the most ideal way that I could imagine about how, post ChatGPT work may look like for, not only for music, I think for all the different industries. Cool.
Yeah, and it's only because your work is so effective that these questions come up, so.
Right, yeah.
Okay, let's let the audience leave and
Okay.
thank them again.
Yeah, thank you.
Thank you.
Yeah, thank you all for joining.